Okay, so the first problem I'm going to do, I call the easy route problem. So I designed kind of an arbitrary source routing protocol, which basically takes your data, encapsulates it with this header, and sends it through a series of switches. And that's source routing. So the sender is responsible for adding all the pass information to the packet when it sends it. And then each header along the way is going to look at the relevant information, take it from the header, and then pass it on to the next switch. So this header consists of a preambles of 8 bytes of zeros. So this is just so in case you have like parasites, Ethernet packets going through the topology, you can just drop them because you only want to be routing the source routing packets. And I'm pretty sure it's very unlikely an Ethernet packet is going to start with 8 bytes of 0. And so the second field is a 32-bit integer, which is a number of hops and all the paths. So 32-bit is going to be a bit too large, but whatever. And then we're going to have like a succession of bytes. Each byte identifies the outgoing port for the switches. So this one here is going to be the outgoing port for the first switch. This one is going to be the outgoing port for the second switch, and so on and so forth. And at the end you have your payload. So just to be clear, because I think I had these questions at SIGCOMM, there's no Ethernet header or anything. I mean, the only header we have for your data is this source routing header. This is not like working over Ethernet or anything. And you do not have to worry about decapsulation at end hosts because I'm providing you with scripts which are actually going to do that. So basically, when you send the packet, I have a text file where I describe the network topology, then we can just run the shortest path algorithm on this topology, and so the sender, based on the destination, knows which path it's going to use. So I'm doing this, you don't have to worry about it. And so I think, this is the topology we're going to use. So 3 switches and 1 host per switch. And if I want to send hello from H1 over there to H3, this is what the packet is going to look like when it's leaving H1. So the sender, my script, is going to do this encapsulation here. So we have our 8 bytes of preamble. Then we know we have 2 hops, which is switch 1, which are switch 1 and switch 3. And so on the first hop, which is switch 1, the outgoing port is going to be port 3, which is why this byte is 3. And then when I get to switch 3, the outgoing port is going to be port 1, which is 1, which is way 1. And don't worry about the encoding of the string or anything, just and so when it leaves at switch 1 has to decrement the number of hops and has to remove the first part of the list. So this is a packet when it leaves at switch 1. By now you probably have guessed this is a packet when we leave switch 3 on port 1. This becomes 0. We no longer have a port in the port list because the number of hops is 0. And this is a packet which is like expected endpoint. So basically, a valid packet for any host that the host is receiving follows this format. 8 bytes of 0, 4 bytes of 0, and no message. And then it's going to strip, my script is going to strip this away, and it's just going to display it on your screen so you can check it out. Should I demo the solution so that you see what's going on?
I think so.
Okay. So, yeah, on the VM that you get in home directory /tutorial/sitcom/source routing, you're going to have all the instructions that you need to do this exercise. And in particular, you have the steps to make it work, and you also have a tarball with the solution files. So, if you're stuck, obviously it's better to ask us. Wait a little bit until you look at the solution. And also there are like many ways of writing a solution for this. There is no one correct way. So if your thing is working, it's not the solution is perfectly fine. And I'd be happy to debug your code if it's different from the solution. So don't just take the solution, we can work it out together. Okay, and before we start, I'm going to talk about the second problem because everyone's going to work at a different rhythm, especially those of you who already have done the assignment. And so, by now, between yesterday and today, I've heard about TCP Flowlet switching a few times. Let's just recap, it's going to take 2 minutes. So the idea is to leverage the burstiness of long TCP flows to achieve more accurate load balancing. So in the exercise, we're going to start with regular ECMP implementation. And by the way, I know that Vladimir has been talking about action profiles, but this implementation doesn't use action profiles, which actually makes it like easier to read. So it should be pretty straightforward. And then I'm going to send like one long TCP flow, and because we're using ECMP and we're hashing on some fields in the IPv4 header and TCP header, all the packets are going to take the same path. Obviously, this is how ECMP is working here. However, if we use Flowlet ID, what we do is we add this Flowlet ID, which is like an integer, to the list of hash fields we use to select the next hop. And which means we're going to add some entropy to how we choose the path for each packet. And so now the path can potentially change between two packets. And the way we determine whether the path is going to change or not is if we have a gap greater than 50 milliseconds between two packets, then we're going to increase the Flowlet ID, recompute the hash, and if the hash is different, we're going to select an. And so we use 50 milliseconds here. In the data center, that would be like much slower than we're working on the laptops in the VM. So 50 milliseconds sometimes to observe interesting things. And so this is kind of some pseudocode of what's going on here. So we compute a hash over the 5 tuple. So IP source address, destination address, protocol field, TCP source port and destination port. And computing this hash gives us a flow ID, flow index, which is going to be the same for all packets in the flow, obviously, because this byte double is not changing. And then we're going to have two registers that Vladimir talked about. In one, so both of them are going to be indexed by the flow ID. So you can see it as an array, and each cell in each array is dedicated to one flow, one TCP flow. In the first register, we're going to keep a timestamp of the last time we saw a packet, and in the other one, we're going to keep our Flowlet ID. And then we just applied what was on the previous slide. So every time we receive a packet, we compare it to the last timestamp by querying our register array. And if it's greater than 50 milliseconds, we increase the Flowlet ID. Then we recompute the CRC16 with the 5 tuple plus this Flowlet ID. And we're going to get some hash which is going to give us ECMP next time.